Okay. Now, so far we have discussed about analysis of stress, analysis of strain. So, this is the last slide we have discussed. The discussion was carried out in 3 parts. Okay. This is the initial part, then we discussed about principal strain, principal direction, some problems, strain compatibility. This is what we already discussed. So, the next part is establishing relation between stress and strain. So, for that today we will be discussing about material properties. So, because that is the relation we require to establish this stress and strain relation. So, these material properties, what are the properties, how we determine them, that we will discuss today, first part. And in this connection we will again discuss about the measures of stress and strain which we observe phenomenologically. That means from some experimental observation we get these material properties. So, in experimentation there are some measures. So, there are stress measures, strain measures. That is what we will be discussing, and the idea of true stress, true strain, those things also we will be discussing today. Okay. So, let us go into the slides. So, here this is the slide, first one we will be discussing with that. So, now this particular slide is downloaded here. Let us go into the download one. Let us open this particular slide first. Okay. The material properties. So, now the material properties in general, there are various types of material properties, okay, out of which see here there are physical properties of material, can be electrical property, magnetic property, etc., etc. Out of which what we require is basically this mechanical property, okay, for our discussion. And again, these properties, there are various types of engineering materials. Those are, in general we will be discussing about metals, but nowadays there are ceramics, polymers, composites, other type of materials also. Now, the question is, for a particular material, again the manufacturing procedure or the processing of that particular material, that affects the particular property of the material which we are going to measure. Okay. So, here you see, for a particular material the property depends on the structure of the material. This means a particular material can have different types of structures. You recall iron carbon diagram. Okay. So, this comes from our atomic structure, other things, okay, that is there. Next part is the process, structure property. This process is basically the process through which the material has undergone. That means a particular steel you can annihilate, you can quench it. Okay. There are certain manufacturing process, say casting, or say there is welding sort of thing, that is not a homogeneous thing, okay, casting, rolling, etc. So, these type of operations, manufacturing processes, they also affect the mechanical property. Okay. So, so this is what affects our mechanical property. So, this is what we must take note. Okay. That is understood. And finally, determining the mechanical performance of the material. So, we will be discussing about mainly engineering materials And as mechanical engineers, our discussion would be mainly on these type of materials, not much on semiconductor materials, where metals, ceramics, polymers, composites, etc. In general, which are homogeneous, we can take those materials are homogeneous, not like concrete or other things which civil engineers use as such. Okay, that part we would be discussing. Now there are these two properties. Homogeneous means a material means if it has same composition at every point in the body in general. Now a homogeneous material may or may not be isotropic. This isotropic means this is the property that a material has identical property in each direction. Okay. So usually those properties are not valid for this composites material. The composite itself indicates that the material has different property in different direction. So these are preliminary idea about material property. And in material design, although we are not going to design a material which is in the domain of metallurgy people or material science people, they work on that. But what is the idea of material design? This is basically to improve property of material. Say for example, if we like to enhance strength of the material as well as to enhance its energy absorbing capacity. Okay. In that case, a particular material has a measure of ductility, which is the measure of its deformation capability. Okay. So that way, stress into strain, that gives us energy per unit volume. So if we use that particular sort of plane to represent a material property, say this particular line represent a material property in strength versus say ductility plane. Then the material scientist, he will try to improve the property, which means this particular line will try to shift in this. Okay. Now we know that there are certain operations, certain structure, whatever, by which we can improve this property. So this is material design paradigm, but this is not what we are going to discuss here. Yes, you have any question?
Oh, sir, what is meant by paradigm?
Oh, okay. Okay then. So now we see. So this is what we have already described. Okay, what is material characterization depends on its structure, the type of particular property we are going to discuss, then the process through which it has undergone, okay, and the performance which we are interested with. Now in general, the type of material we are going to discuss, they are solids. We are not going to discuss about fluid or gaseous materials. And again, among solids, mostly we are going to discuss about metals. So ceramics, polymers, composites, they are not discussed here in details because each of them require a separate discussion. We will be discussing on metals only. Okay, material properties of metals. So these metals, they are characterized in general by a crystalline structure. So there is basic crystal structure for metals, although not all, say for particular type of cast iron, etc., there might not be any crystal structure. It can be amorphous also. But still, for metals, they are characterized by these things. What it is, atoms are located, actually this is located regularly defined repeating position. This is the feature of a crystal, but in general atoms are closely packed. Okay, that is there in metal. structure has free electrons, making metals good electrical conductors. That is, they are strong, strength is high, and density is also quite high. Dense means higher density. Now, their temperature resistance is moderate. Actually, this is a general term. What is meant by moderate? Okay. Say melting point is a measure of this temperature resistance. And metals resist brittle fracture by bending, but again there are certain materials which are brittle, like cast iron again. But in general, metals are ductile. That means they can take up some amount of deformation before failure, which is the measure of ductility here. Okay, this is what we will be discussing, and then see what is the role of this mechanical properties or this material characterization, because what we are going to discuss here is mechanical properties of materials, and these properties are needed to establish the relation between stress and strain. Okay, because this particular equilibrium equation we have developed for stress stress analysis. Basically, force and stress, how they are related, how we represent stress, etc. And also we have discussed about the strain and displacement relation. From displacement field, how we obtain strain field. Now next we will be focusing on stress strain relations, and here we need this mechanical property. And where from this mechanical property will come? They will mainly come through a load deflection test. At a material testing, there are different types of material testing, but we will be focusing on load deflection test primarily. Now, this is what we have seen in the very beginning. Okay. So, that means our description is related only in this area, in elastic domain, and in this other domains, these are some of the phenomena which we get in plastic, elastoplastic, rheological domain, etc., etc. So, I think this is what we discussed initially in some cases when we are characterizing the subject area in which branch of solid mechanics this our stress and deformation analysis is included. In that connection, we discussed this slide earlier also. This one, this is some description of material in these domains, plastic, rheological, etc., etc. So, this is what we are not going to discuss here within our course. So, depending on this type of material characterization, we get different types of materials, isotropic, orthotropic, like ceramic, etc., etc., and other material properties like creep, plastic deformation, viscous deformation, from this type of diagrams, which are basically related with plasticity or rheological studies. So, our focus is mainly on isotropic material, isotropic homogeneous material, as mentioned in the first slide. So, this is the initial part. Okay, with this idea, we now go into our stress deformation analysis. You know about the machine, testing machine, in which we carry out the stress and deformation analysis. This is known as the universal testing machine. Nowadays, the machines are connected with a computer, so the results from this machine is stored. We get them in this computer memory directly. And in older machines, those were noted manually from some deformation and from some load. So, in this connection comes the measure of the load and deformation. Okay. So all these things, this stress and deformation analysis, experimentation at least say, or their relations, they basically came from the observation of Hooke, Robert Hooke. Okay, and he was a Britisher, a British physicist, based in London basically. Okay, and he has first reported this relation, which is the linear variation between tension and extent. Tension or the applied force, tensile stress with extension. Okay. Or we can say this is basically the observation of a linear relationship between stress and strain. So, first reporting by Robert Hooke was made in 1678, although this observation was made many years ago, around 1670s or something, whatever. So, this is Hooke's law, stress-strain relation, which is a linear variation according to Hooke's. But now we have seen that our stress, our strain, they are not a single quantity. That means they are not necessarily linear, means unidirectional stress or strain. There are shear stress, shear strain, etc., and the stress and strain are represented by a matrix, 3 by 3 matrix. We call them stress and strain tensor. So, the relation which describes this stress tensor with strain tensor, that law is again named after Hooke. This is Hooke's law, but to distinguish with a linear variation between unidirectional stress and strain, they are in general called the generalized Hooke's law. Okay, so this is what we use now, generalized Hooke's law. So this material constant, when we have some material constant coming from Hooke's law, from some generalized Hooke's law, whatever, this gives us the stress strain relation. So this is what we will obtain after we find out these material constants or material properties. And what next? Whenever we have this stress strain relation, this will give us the equilibrium equation which we derived in our stress analysis discussion, that we will describe in terms of displacement field. Okay. So, this is what is required for solution of the problem. So, once this is established, when we have the equation of equilibrium through displacement field, then we will go into the problem solution. Okay. That part. Now, here you see in this tensile testing machine, okay, in this tensile testing machine, first thing is we need a specimen. Specimen for tensile test of the particular material for which we are going to establish the material property. So, in general, the test specimen, they are not arbitrary. That means they are not taken from any source. Why? Because we have already seen that there are various elements on which the material property depends, is it not? There are structure, the particular property, the process, the performance, etc. So, that is known to us, and that is why these specimens, okay, they are special type of specimens which has gone through a specified manufacturing procedure, okay, which has a specific dimension, the surface condition is given by certain surface roughness values, etc., etc. So, following those standards, Actually, we are not going into the details of this universal testing machine. That will require a separate lecture on the testing machine only. So these are standard specimens. So these specimens, they are put inside or within the machine, in this machine. So they are the arms, you can say, crossheads of the machines, right? So these one here in this particular machine, one is fixed, the other one is moving. Usually it is like that, okay, and then these crossheads are connected with some grips, okay. There are one movable crosshead, this one is movable, other one is fixed, so they are connected with some grip, and in between these two grips our specimen is put. There are various types of mechanism through which the specimen can be inserted within the grips actually. Here it is threaded, but they can be a friction grip as well. This way. And now what next? Next part is some load that will come, okay, on the movable grip. In this particular machine, what is the mechanism by which this grip will move? So this grip will move by this screw, you understand. This is our conventional universal testing machine also. They have this type of drive which ultimately comes from, actually that is one type of mechanism. Here this movement comes from this hydraulic cylinder, okay. So this is the power bank which contains the high pressure fluid, and when we release the valve, the fluid pressure goes through this ram and this cross arm, okay, that applies the particular force to the specimen, and there would be some elongation to this particular specimen from movement. So what we measure from here? We measure displacement of the specimen between two specific points. This is clear. First one is we have a standard test specimen. On that particular test specimen, we mark 2 points, and in between these 2 points, the distance is known as gauge length. So this particular geometry is always specified, what it would be, how it would be. So now what we need to measure from here? The distance between those two fixed points. You see there are some measure, okay, some arrangement by which the distance between these 2 points, they are noted. So that mechanism is known as extensometer in general. Okay. There are different types of extensometer. Again, we are not going to discuss that. And other part is the load, measurement of load. Okay. And of course, we need to measure the change in diameter, because this particular specimen has a specified gauge length as well as it has a specified diameter. Specified diameter, specified gauge length, and during deformation this diameter changes. Okay. Here this is appreciable because this is known as necking, when necking starts, and ultimately it will fracture also after necking starts. So this change in diameter, measure of this d value, d0 value, this is also important. Then how we measure strain? This is known as extensometer. We can measure it using a strain gauge. That is, we will be discussing strain gauge afterwards. Right. We can also measure it by the movement of this particular crosshead, how much amount it has moved, that displacement, that we can measure. If there is no slip between this grips, then the amount of extension of this specimen is equal to the movement of this particular crossbar. So these are the measures for the displacement. Okay. The other measure is the load. So for measuring this, we can use load cell. This load cell means something. Here you see this is a sort of load cell here, or it can be there on top of that also. Or here in this case, if the diameter of this plunger or piston rod, they are known. Okay, and we know fluid pressure, then also we can determine what is the load. So that way this is what we measure, and from there what we plot is the magnitude of load, okay, which is applied at the grips, and then the change in gauge length. Okay, that is the elongation. So this load elongation plot, this is what we observe. This is experimental observation, and then we express this in a stress versus strain diagram. So here, this particular plot, stress strain diagram, is taken as the basis of the material property. Why? That is also quite clear. Say there are load displacement diagrams or load extension diagrams. This is not a unique property for a material, because if we change, say, the gauge length, here you see the first one has 2 inch gauge length, this has 8 inch. Okay. Or if we change the diameter, we can change gauge length, we can change diameter. The first one has 0.2 inch area, that means its diameter is something such, and here this is 0.3 inch. Although the first and third has same gauge length, their diameters are different. So in such cases, the load deflection plots, load elongation plots, they will be different. This is indicated here. Okay, circle mark means this one, then triangle means this one, whatever. But then when these diagrams, they will be transformed into stress strain diagram. So how this transformation is done? Applied load divided by the area. Now here again comes that question, which area? Now we see this diameter, this is also changing, it is obvious from here. So let us take this is original area, right? We get a stress value. Taking that measure, we get a stress value, and there also, if we measure the elongation and we express that elongation in terms of this gauge length, then this is a measure of strain.
Yes, sir.
Change in length, change in gauge length by gauge length is a measure of strain. This will give this type of diagram, which are known as engineering stress strain diagram. Okay. So this engineering stress strain diagram, which we use in ordinarily or if in our undergraduate studies also, deal with stress strain diagrams. So this implies that it is an engineering stress strain diagram based on that gauge length and cross-sectional area of the initial specimen, original specimen. But then there are certain other measures which will give rise to other types of stress and strain measures. And what we observe is that if we measure, if through some other techniques, through some other way the stress and strain is measured, the change in this stress strain diagram up to elastic limit, which we call as the yield stress limit. Okay, the change in result is negligible, but then the change is appreciable beyond this elastic limit. So, beyond these points, beyond this point, the changes are appreciable when we measure stress and strain by using some other measures. Okay. This is what we are going to discuss now. Now again, this specimen was for a particular material. If we change the material, if it is another type of material, the nature of this stress strain diagram, it will also change.
Yes.
So these are some diagrams. What we observe from here, in this particular case, there is not much extension, but it fractures, the failure occurs. And here the same failure occurs after large amount of extension. So this is known as a pure brittle character of the material, that you know, and this is known as a pure ductile characteristic of the material. There can be some material which is somewhat in between this brittle and this ductile property or character. And then let us define this, what is important from this figure is this particular term, offset yield. What does it signify? See, in the stress strain diagram, the maximum value of stress which we obtain in that particular diagram, that is known as ultimate stress value, okay, which we take as a material property from this diagram. And this ultimate stress value is different. For a brittle material, fracture occurs at ultimate stress value, but for a ductile material, ultimate stress value is not the fracture stress value. Fracture occurs at a different point. And what is the yield stress? In general, yield stress gives us the elastic limit of the material.
Yes.
That means, if we cross this particular stress value, the material loses the property of elasticity.
Yes.
Now, it is not that the material property up to yield stress will follow a linear relationship. Okay. Now, you note here this particular test, it follows the experiment of Robert, because here the stress field is uniaxial, the strain field is also uniaxial. This is a relation between sigma xx and epsilon xx. Okay. And as Robert Hooke predicted, the relationship is linear. Here also we get a linear relationship, but what happens when we are close to this yield stress value, right? After a certain value, the linear relationship is no longer valid. The relationship between stress and strain, it can become non-linear. Okay, but still the material remains elastic. That means, if the stress value goes up to this point, which is known as yield point, and corresponding stress value is yield stress, it will come back. That means, the deformation or the elongation there, it will become 0 when we will release the load.
Yes.
So that is why there is a difference in these points. This is known as proportional limit.
Yes.
That these things you know from your undergraduate studies. then actually this purely ductile materials has a marked yield stress value, but what is this particular value y here? Okay, sometimes the elastic limit is also the y value, that means yield stress value. But what happens for this type of material behavior, which is say in between this brittle and ductile nature? If it is ductile, then this is a marked yield stress point is there, but here we don't have any marked yield stress value. So what is done here? Okay. So this is our stress strain diagram. Right? This is the experimental stress strain diagram. Now here on the strain axis, we take a value of 0.2%. 0.2% means 0.002. And from that point, we draw a line parallel to this line. That means where our stress strain relation is linear. That is quite obvious from here. Taking that particular slope, okay, we can draw a line, and this particular line will intersect our stress strain diagram at a particular point, and we take that as the equivalent of yield stress. So for such a brittle material, actually there can be some cases when this won't go up to 0.2%. Actually this is also known as a proof stress. There are 0.1% proof stress, there are 0.2% proof stress, etc. But usually offset yield stress is known as offset yield stress. It is specified by this permanent deformation of 0.2%. What does it mean physically? Means if the material is stressed up to this point, and if we release the load, then it will not come back to a zero strain value. There would be some amount of deformation we will get, but that value would be 0.2%. This is known as y value. So that is why we have a y point here also. So this is what we get from a stress strain diagram, and let us note what are different observations from here. What we get, the maximum stress value point known as ultimate stress, also called ultimate strain. This is the yield point, whatever, elastic limit, y limit, whatever. This gives us yield stress and yield strength also. This is the rupture value. Okay. What is rupture stress or fracture stress? This is from where necking starts. Okay. Necking, you understand what is necking from the diagram, when the change in diameter is quite appreciable, so necking starts. Now strain hardening part is something like this. You see, after yielding there is a slight change in stress strain diagram. First from this point, this is drooping nature, but then again this part here, the stress is increasing with strain. So this part of the curve, okay, this part is known as strain hardening. Okay, but here you note that beyond this yield point, if we are in this region of this curve, there would be permanent deformation. Permanent deformation means if we remove load from this point, okay, the material will follow this elastic line to recover the stress. That means from any of this point it will come back following this line, and you find out where it will come. That part on this stress strain axis, that will remain as the permanent deformation in the material. So this part is strain hardening, and then there are other type of materials also where we get strain softening also. This particular nature beyond elastic point, okay, this nature is known as stress hardening. But for this type of nature we say this is strain softening. So beyond necking we have that stress softening part. And this particular point is ultimately this is fractured here, and from this point necking starts. So this is plastic deformation. From this point what happens is reorientation in the crystal structure. In the microstructure, some directions of those microstructure, they are changed, they orient themselves to oppose the load. Okay. So that is why we get this strain hardening part. And when that limit is exhausted, no more reorientation of crystals is possible. This is the region where the plastic deformation now starts from this point. Ultimately it fractures. And up to elastic point, so whatever we obtain from these points, we get actually two set of values. One set of value along stress axis, another set of value on the strain axis. So, and we understand up to this part this is elastic range, beyond that point this is plastic range. The same thing, this is also we have discussed. These are the properties. So, now the properties which we get from this particular test, those are modulus of elasticity, this particular one, sometimes known as Young's modulus also, because after Robert Hooke, Young carried out the test for uniaxial stress field. So modulus of elasticity is also known as Young's modulus. And in connection with generalized Hooke's law, when we say the modulus of elasticity, it has an equivalent generalized modulus of elasticity sense. That also is the yield strength 0.2. Now, whatever be the material type, brittle, ductile, whatever. Then third one is tensile strength or ultimate tensile strength, the maximum value. The ductility measure is this one along this axis. Okay, this is ductility measure. How much elongation it can take. And this is the toughness, means how much energy the material can absorb before fracture. Area under stress strain. So these measures are along stress axis, and similar measures we can take along strain axis as well. Okay, these are sort of things. And coming from these observations, we can get some more values. Okay, like bulk modulus, etc., etc., and there are some more tests through which we can find out shear modulus, or Poisson's ratio comes from this particular test as well. Okay. When we measure the change in diameter of the specimen, we can also measure the Poisson's ratio. We will see what it is. It is known to you as well. This is Poisson's ratio, right? So, we measure change in length of the specimen as well as we measure the shortening or the change in cross-sectional dimension of the specimen. So, the ratio or negative of the ratio, because usually this change, if this elongates along axial direction in a perpendicular to it, that means in transverse direction there is a reduction. So, this that is why this is expressed as minus of this, so that the value is positive as such. Okay, this is understood. This is another material property, Poisson's ratio. And then this is the measure of toughness, how much energy it can absorb before fracture. So that way it is. Brittle materials, they give high stress value in general, but their toughness is low, and that is why if you drop a cast iron product from an appreciable height, there is a possibility that it will break. But for high ductile material like this, okay, their strength is not that much, but then it is very difficult to break them by dropping it, by nature, by some nature of impact force. So these are some of the material nature of stress strain diagram for different materials. Now the nature of failure for brittle material, this is how it will look. Okay. So this is in tensile testing, this is how the failure of brittle material and ductile material will appear. And then there is another test which is known as torsion test of a material. So in torsion test, there are two grips, but it is not a tensile load which is given through these two grips. Rather, one grip is fixed, the other grip is rotated. So you are giving a torsional loading, applying a torsion on the specimen, and there would be failure ultimately. Again, the nature of failure for ductile material like mild steel and a brittle material like cast iron, they would be different. There are some more material properties. Hardness is another property, okay, which is measured by some indentation. Some indenter is used to measure hardness. The toughness part, here also we use toughness part, and some more material testings are there, okay, like 4-point bending test. Now you see what is written here, this Lami's constant, volume dilation and bulk modulus, this is what we calculate. Actually, this is what we have discussed in our last class, right? So the volume dilation means volumetric strain. From strain tensor we can measure this volumetric dilation. And then from our stress analysis we had an idea of hydrostatic pressure, uniform stress you can say, and their relationship, that hydrostatic stress and our volumetric strain. Okay. So P by delta. We represented hydrostatic stress by P and this volumetric strain by E. So that P by E, this gives bulk modulus.
Yes.
Okay. So this is what we get from the measurement. We also get Lami's constant. So you note that this Lami's constant is not what we get from material testing. So this is derived through some mathematical manipulations. Okay. So you can say these are mathematical constants. Okay, but still they are used as material properties. Okay. We will talk about those constants afterwards. Now this 4-point bend, this is a measure of this, say, amount of deformation that the material can withstand. Okay. Now the measure of ductility is measured through percentage elongation and percentage reduction of area. So this you know, percentage elongation is final gauge length minus. Now how final gauge length is measured? So this is initial specimen and this is the specimen after fracture. Okay, there was necking in this region, then it has ultimately fractured, and still these markings they will be there in the fractured part, and after fracture these two they will be matched once again. We will measure what is the distance between these 2 points. So this is how we measure the final gauge length, okay, after failure. As well as we can measure this diameter is known of the initial specimen. At the point of fracture we can also measure what is the diameter here. Okay. So from this diameter we can calculate what are the areas. Okay. So percentage reduction of area by original area. Okay. That is also a measure of strain known as percentage reduction of area, percentage elongation. These are measures of ductility. Okay. That's fine. Then there are the measure of toughness, which is a measure of the energy it can absorb before failure, you can say. And there is another measure which is known as resilience. So what is the difference between toughness and resilience? Toughness is energy absorbing capacity up to fracture, and resilience is the same capacity, but this is up to the elastic limit. That is also known to you. This is hardness testing is there. Different types of hardness testing are there. In Brinell hardness testing, a spherical ball is used. There are Rockwell hardness testing also, where some pyramid form of indenter is used. Then there are different scales, etc., etc. This spherical ball diameter can be different as well. And then we measure what is, we apply a certain load. Again, all these testings are specific testing. These are not arbitrary. You cannot apply any arbitrary load. There are certain load scale. Accordingly, the BHN value has different scales. Similarly, this particular indenter, this is made from a specified hard steel. Okay, that is specified. The diameter is specified. What is measured here is the magnitude of indentation by this ball when it is pressed by certain magnitude of load. And by measuring that particular diameter, one is initial diameter, other one is the impression that it will leave on the specimen after the test is carried out. This is how it is calculated. And you see, for different materials, this is the variation of this Brinell hardness number, this is Brinell hardness number. And for different, say, steels having different carbon percentage, okay, that means from mild steel to high carbon steel, and for different type of processing. What happens? Tensile strength, if they increase, these are the tensile stress values, range of tensile stress, this is yield stress, they are related somewhat. With increase in tensile strength, tensile stress, here BHN values increase, here also BHN values increase with increase in tensile strength. So this is an indirect measure of, say, the stress value in the domain, although there is a question that this measure is a surface measure. whether this is valid in the domain, that is a question. So there are certain relations which probably in your contact mechanics you have some discussion on that. Okay. Okay, other type of material modeling is there. Anyway. So these are some of the measures which we carry out. So with this idea, now let us go into the discussion on, let us stop here and then we will go into the discussion of true